Hello, my name is David.kimble, and for my presentation, I am reviewing acoustic emissions monitoring of bridges review and case study by Arcana Nair and C.S. Kai. In many states across the U.S., roadways and highway bridges are running into disrepair. Structural health monitoring has become a very important factor to maintaining bridges. To monitor bridges, a non-invasive continuous monitoring system is needed. This journal looks at a less studied method of an ideal passive system of structural health monitoring called acoustic emissions, or AE. This technique has been used for many other structures, but not as much for bridges. Bridges and roadways are under constant cycles of stress as heavy vehicles drive over them. As the bridge goes into a state of stress, the materials such as concrete and steel emit a form of elastic waves. These waves are picked up and measured by sensors attached to the roadways. The acoustic emission system requires a material deformation from a source and a transducer that receives a stress wave signal, this making it an ideal system, as a developing flaw in the material emits a burst of energy in the form of high-frequency sound waves and are received by the sensor in place. Strategies of AE monitoring include local and global. Global monitoring assesses an entire structure's integrity, while local monitoring assesses a specific location of the material. Some of the disadvantages of acoustics are complexity of the noise filtration process. This system is also not recommended for bridges that are not under frequent high-stress applications. The measurement of acoustic emission involves three basic components: the generated AE wave from the bridge, the detection equipment to capture AE signals, and processing and interpretation of the collected data. Most sensors used for AE consist of piezoelectric elements while undergoing transduction. Their primary function is to detect the transient elastic mechanical waves and convert them to electrical signals so that they can be analyzed. Most researchers prefer the use of resonant sensors because they are highly sensitive to AE signals. Most sensors are glued onto the bridge surfaces, and some are now being built into the structure. Preamplifiers are also used, either external or built into the sensor itself. Preamplifiers are used to improve the signal-to-noise ratio. Signals are interpreted to show the magnitude of the stress on the bridge as shown in Figure 4. Interpretation of such signals requires a lot of experience and study. Different conditions as well as different materials will receive different magnitude of signals. Materials found on bridges under a load are known to emit acoustic waves only after a primary load level is exceeded. This is known as the Kaiser effect and is represented in Figure 4 on points 1, 2, and 3. All of these conditions, as well as many more, are to be considered while analyzing the data received from the sensors. The need for two index, historical and severity, are needed to quantify the statistical analysis of the parameters. The historical index H1, given by equation 1, defines a measure of the change in signal strength through the loading phase of that test. The severity index SR, given by equation number 2, is defined as the average signal strength among the largest numerical values of the signal. N is the number of hits up to the time t. S is the signal strength of the ith or mth hit and index. And K and J are empirically derived constant based on the material for historical and severity index. After plotting the historical and severity index, we get an intensity chart as seen in Figure 5. This shows the multiple sensors and how they compare to severity of the damage by dividing the chart into zones of damage. This technology has been developed and studied in the 70s and most recently the late 90s. Now into the 21st century, the experimenters have started to update the equipment along with the process. New, smaller, and more sensitive sensors have replaced the old sensors. Artificial intelligence software is being implemented, as well as wireless technologies to make monitoring much easier without getting in the way of bridge use and without damage. One of the test studies for AE technique was done on a bridge in Louisiana in 2006. This bridge consists of 3 separate equal spans as seen in Figure 6. This test was 3 days long and had weighted trucks weighing roughly 272 kilonewtons or 27 tons running over it to give the stress needed. This test was to determine if a center diaphragm was needed in each section of the bridge. A systematic labeling system was developed for each case scenario. Figure 7 shows the representation of different scenarios. As we can see, one truck is in the shoulder, there is one in the middle lane, and the other has 2 trucks that are in each lane at the same time. In Figure 8, we see the different sensor placements around the girders. Figure 9 shows another arrangement of sensors placed around the girder for the sensors surround the diaphragm. By using selected software, the results are analyzed. Figure 10 shows the results of a handful of tests performed. To get a better look at the severity of the cases, they use the formulas mentioned earlier for historical and severity. Tables 2 show the results for each category per test for that day. Here is another amplitude versus time plot that shows more of a concentrated area. We also see a historical severity chart that has a few sensor readings. Most sensors were not subjected to enough load to register. The intensity chart shows D40-T1L1 sensor is on the high side for most of the tests. This would be a point of interest, although the severity is not concerning. Another case study was performed on the steel structure of the bridge as well, to learn more about the AE process and the condition of the bridge itself. For the steel components, the threshold of the bridge must exceed 40 dB. If under that, the sensors would not pick up the signal. Figures 15 and 16 show the comparison to normal traffic to overloaded trucks. The overload consisted of 2 trucks with trailers that weighed roughly 240 tons. This is a hit versus time chart, and as we can see that the normal traffic load is much lower than the overload. It was determined, however, even though the overload was high, there was no damage to the bridge. This gives the bridge a good comparison to future events or future studies to see what a normal operation would look like. In conclusion, this journal discussed the different techniques for acoustic emissions for structural health monitoring for bridges. As learned in this journal, the most difficult part of the study is to recognize the signals and filtering the noise. This is where experience is a must. Performing tests like these are absolutely necessary and should be performed more frequently. This helps researchers recognize what is normal and what is not in assessing the severity of damages in the bridges. As we know, there are many bridges even here in Oklahoma that are in disrepair. With this technology, we could pinpoint the disrepair wirelessly and keep track of the state of the bridges.